Hey guys, today we will be solving the path integral for the harmonic oscillator. So let's begin. So here's the path integral, and here's the Gaussian integral. And to solve the path integral for the harmonic oscillator, what's going to be helpful is to generalize the Gaussian integral to vectors pretty much. Because like in the last video, we solved it for the free particle, and what we did was we just integrated like over all the various paths, really. And we saw that like each like contribution from each path was a Gaussian integral, right? And that was pretty cumbersome to do. So instead, what we can do is sort of work with generalized vectors, right? And we can look at how the Gaussian integral works for generalized vectors. And to do that, we have to note that some general vector x with an arrow on top can be written as this. This is a column vector. So the Gaussian integral for vectors will have an integral over not just x, but x1, x2, x3, all the way to xn, where n is the number of dimensions of the vector. We're going to have e to the minus x times a times x, where a is some matrix. Now we get this by knowing that e to the minus ax squared can be written as e to the minus x ax. So if we generalize this to a vector by replacing the x with x vector, then we want this to still be a scalar quantity, right? We want to raise e to a scalar. We're not doing any Lie theory here. So if we want this to be a scalar and these are vectors, then A has to be a matrix. We can write this out as a summation like this over here, where there is an implied sum over I and j. Now, how do we get from this to this, you may ask? Well, just by noting that here we have like e to the minus, then like x1, x2, x3, dot, 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 times like a11, a12, a13, dot, 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 right? And then times x1, x2, x3, dot, dot, dot. That's what this is saying right over here. And we're now saying is that, oh, if we're to multiply all of this out, you're going to be left with e to the minus x1, a11, x1 plus x1, a12, x2, and so on. And we can write that as a more compact notation like this. Now there's a nice strategy that I like to use to actually know like what letters each like variable gets is by noting that a is a linear map. So a can be written as aij, ei, tensor product epsilon j, where epsilon is a dual basis vector. By the way, if you guys know tensor calculus, just skip this part. But then what we can do is you can note that we have x, a, x. We can write out x as like say vk, ek. And this x can be written as say va, ea. This means that we have VA, EA, times AIJ, EI, tensor product epsilon j, and then VK, EK. We can move this VK to the front, or like this V, by the way, these are just the components of the vectors. And then when this vector goes to this covector, by definition, the inner product of vectors and covectors in the same basis it's going to be the delta function, jk, which means that k has to be equal to j. We have vj over here, so we have vaea, vj, and then aij, and then ei, right? And then we can let this ei inner product with this ea. That's going to give us delta ia, since or it's really just delta. They should both be downstairs indices. Delta ia, and this is because our basis vectors are defined to be orthonormal. So this means that I is going to be equal to a, so we can change this to I, and then that means that these go away now. And now we have vi, vj, aij, or we could write this out as vi, aij, vj, or just vi, aij, vj, if we don't care about Einstein notation. So that's how we get that. So what we could do now is we can write this matrix A in terms of a diagonal matrix D multiplied by an orthogonal matrix Z. So basically what we're doing right now is we're saying, okay, let's write A in terms of a diagonal matrix, and that transformation will be described by this over here, where Z is an orthogonal matrix. So now what we can do is we can write this out as d to the nx, where d to nx is just defined as this over here, and then e to the minus x vector z transpose dz, and then acting on x. Then we can define the y vector to be z acting on the x vector, so z is going to be a linear map. So this just gives us y vector acting on this over here. This should technically be transposed, but let's not be too picky. And this integration measure is going to turn into d to the n y. The reason that it's 1-to-1 is because since z was an orthogonal matrix and y was defined as the orthogonal matrix z acting on x, this means that dy is going to be dx. Since orthogonal matrices, they have a determinant of 1. Since the determinant is 1, that means the area isn't going to change under transformations. So that's why we're going to have dy is going to be equal to dx. And our orthogonal matrix, by the way, is a matrix that's defined as this over here, where the transpose of the matrix multiplied by the matrix equals the identity matrix. And we can just expand it out like before. So we have yn, then e to the minus. Now we're going to have dii yi squared, because D was defined as a diagonal matrix, and diagonal matrices, they're defined as matrices that only have elements along the diagonal, so everywhere else is 0 on the matrix. So that's why we have this over here. And now you guys can see the reason as to why we want to work with diagonal matrices, because with diagonal matrices, the indices on the bottom will always match, which is going to be pretty helpful. If you like replace like x with like yi, and then a with like dii, this is going to give us the square root of pi over d11 for this one over here, multiplied by square root of pi over d22, the result of integrating over like each component of y. And now we can see that this is the same thing as the square root of pi over dii to the n. And we can note that the product of dii with itself, it's just the determinant of d, right? Because since D is a diagonal matrix, so like D11 all the way to Dnn, the determinant of it is just going to be the multiplication of everything on the diagonal, which is what we have right over here. This means that we can just write this out as the square root of pi to the n over the determinant of D. And technically speaking, to be mathematically notationally correct, this should have been written as like square root of pi to the n over this right over here, since we have to multiply it over like each index of D. If we want to integrate a multi-dimensional Gaussian integral, which is what we're doing, it's going to be equal to the square root of pi to the n over the determinant of some matrix D. So here we have the potential for a harmonic oscillator. This means that the path integral is going to be this over here, where here is the Lagrangian, which is the kinetic energy minus the potential. We are in the potential as this over here instead of 1/2 kx squared, so that we can factor out the m as we've done over here. We want to have like q times something times q. We don't have that right over here. So what we can do is we can do integration by parts in this integral over here. So just focusing on this integral right over here, we see that we have integral of dt of q dot squared for this one over here. Now we can write this out as the integral of dt q dot times q dot. And now we can use the di method, which is integration by parts really. To do this integral, we can take the derivative of q dot, and the integral of q dot, the derivative of q dot is going to be q double dot, the integral is going to be q, so this integral over here becomes q times q dot minus the integral of q double dot times q, or just q dq over dt, minus the integral of dq over dt, second derivative, times q. We do have to integrate this part over here. Now let's say that we're integrating from t equals 0 all the way to some time t, okay? And we're going to assume that this part over here goes to 0 in that in those bounds. So what we're saying is that we're saying that q of 0 is going to be 0 and q of t is going to be t. And these are boundary conditions on the positions of the particle, okay? And because we have these boundary conditions, we can expect there to be some quantization behavior that's going to happen. So basically, we can just rewrite this integral over here as this one right over here with a minus sign. And this means that we can rewrite this as this over here. And then we can take this part in the integral and we can just factor out q from both sides, leaving us with minus second derivative of q with respect to t minus omega squared and then q. Actually, there should be no q right over here. It should just be the second derivative operator. So you can just rewrite this as this right over here. And then what we can do now is we can distribute the m. We can put the m in here as well. So this means that this integral just becomes integral over q of t e to the I over 2 times the integral of dt, and then we're going to have q m times this over here times q. You can now just rewrite this part as minus 1 over 2i so that we can make this be negative. And now this is in the form of this over here. It means that this answer is going to be the square root of 2 pi I over the determinant of, well, what's our matrix here? Well, in this case, right, A was sandwiched between x and x. So here we have this sandwiched between q and q. So this over here is going to be our operator A. So the determinant of A. That's our answer. We're pretty much done, but not really. Because you have to figure out what the determinant of A is going to be. And you guys might wonder, why are we able to apply vectors to functions here? Like, how is that allowed? The reason is that functions are pretty much infinite dimensional vectors. So we can apply this Gaussian integral, this multi-dimensional Gaussian integral, to the path integral. And now we have to find out what the determinant of this is going to be. But how does the determinant of an operator make sense? So this over here is an operator. And we can map operators to matrices by taking the exponential value of that operator, right? So just like, say we have some general operator. Let's call it like O, all right? And O is like, say, d over dt plus 4. We can actually represent O as a matrix. And to do that, we can write that O of nm, or just O and m, is equal to the inner product between O sandwiched between psi n and psi m. Where psi n and psi m, these are orthonormal matrices that are eigenstates of O. We can just sandwich A between like some two general states, psi, okay? And that's going to give us A and M. And we can write this in a product as psi n and then lambda times psi m if psi m is an eigenstate of the operator A, where lambda is the eigenvalue. We can move the eigenvalue lambda m sub m to the front, and then we get psi n psi m over here. And again, this is all equal to A and M. Now, if these are orthonormal, this means that this gives us the delta function of nm, and this implies that m equals n, which means that A is going to be a diagonal matrix. And since A is a diagonal matrix, that means that we can use this formula right over here. Before we had that it was D, right? But we can use this formula since A is going to also be diagonal. A and N is going to be equal to lambda N. This means that the determinant of A, well, that's just going to be the product of lambda N all the way to big N. Okay, because like just think about it. A can be A is just A11 all the way to A big N, and since A like 1 1, that's just going to be lambda 1. Here it's going to be lambda small n. The determinant is going to be lambda 1 times lambda 2 to lambda n. So the determinant is just going to be the product of the eigenvalues. Now we can map that onto this differential operator because here is our operator. So the determinant of this operator over here is just going to be the product of the eigenvalues of this operator. So to find the determinant, all we have to do is find the eigenvalues of this operator and we'll multiply them together. And by the way, this should of course be to the power of n. And we could actually move m over here to make it not be the definition of the operator. So if we do that, then m would be the denominator over here, and the m would be omitted from this operator. So let's let this non-trivial part be the a operator. And what we want to do again is to find the eigenvalues, okay? So we have to set up this equation. A acts on psi and gives us the eigenvalue times psi. So what we can do is we're going to distribute the psi in here. So you have minus omega squared psi, and then minus lambda psi equals 0. So now what we can do, we can factor out the psi. So minus omega squared plus lambda psi equals 0. And then we can define some constant k. Let's not use k. Let's use p. Okay. So let's define p as being omega squared plus lambda. Actually, no, p squared works better. So p squared is omega squared plus lambda. This means that this over here minus p squared psi equals 0. We can use the ansatz psi equals e to the p or e to the rt, which means that r plus p squared equals 0, or that r equals the square root of minus p squared. So this means that psi is e to the ip, or e to the minus ip. T, I have to add a t there. We can write this general solution out as a e to the ipt plus b e to minus ipt. And yeah, and we can see that the eigenvalue lambda, right, if p squared equals omega squared plus lambda, this means that lambda is p squared minus omega squared. Okay, so this is the eigenvalue, right? But it's not particularly meaningful since p was defined as this, so we can't really get much information out of it. So to get actually meaningful information, what we want to do is use our boundary conditions. Because remember that we said that q, up here, we said that q goes to 0. Okay, maybe it's not here anymore. But we said that q of 0 equals q of t, big T, which is 0. So basically, we were trying to find the path integral, the propagator, the probability that the particle starts at 0, at time t equals 0. Okay, so at time t equals 0. So t equals 0. And then it ends at 0 at time t equals big T. So the particle just doesn't really move at all. Or it can move, I guess, but when we measure it again, it's at the exact same spot. This is the particular propagator that we are trying to calculate. So we can use this to actually extract some physical information. We can rewrite this as a sine of pt plus b cosine of pt. And since q of 0 is 0, this means that, actually, it's kind of funny. we should be writing this out as q instead of psi. I'm used to writing it out outside because of quantum mechanics, but it should be q. And the reason why it should be q, because remember, we said that like psi n, a hats, psi m was like a and m. These vectors in this case, since remember that we said the q, like remember over here, we were saying that q was a vector, like these were vectors, right? And we were replacing this with q. So the vectors that we should be using should actually be q of t, which are functions. Q instead, just replace all these sides with q's. So basically, we would end up having q of t equals a sine of pt plus b cosine of pt. And then posting these boundary conditions, we have that 0 equals a sine of 0 is 0. And then, so we get 0 equals b, okay. And then we have to plug in the one for t equals big T. So q of big T equals a sine of p big T, which equals 0. This means that pt equals n pi, since for n pi, sine of n pi is 0. So this means that p equals n pi over big T. If you guys learned about quantizing the infinite square well, this calculation is probably very familiar to you. That's actually why I used psi on accident. Anywho, so this means that lambda, right? Lambda is p squared minus omega squared. So lambda is just going to be n pi over t squared. So n pi over t squared minus omega squared. So now we have actual like meaningful values in lambda. And we can just stop here. We could do some normalization to find a, but that does not matter to us because we only want to find the eigenvalues, which we have just found. So basically, we're pretty much done here. And yeah, that's our determinant. So we could just like plug that in here, and we're almost done, but there's a small problem here. Recall that for the path integral, you have to note what this curly d thing is. So this over here. We have acted as if this is equal to this over here. We have q1 to n of dqi, I guess. We've acted as if this was the definition for the path integral measure. Okay, but it isn't, right? This is just an n-dimensional measure. But the path integral isn't just multiple dimensions. There's much more to the path integral measure. The path integral measure also includes a factor of m over 2 pi I delta n over 2. And technically it goes to n minus 1. So really, in this calculation, right, we should multiply by a factor of the m over 2 pi I delta n over 2. Because here we had it as if we didn't have this factor, so we should add that factor in the end. And the fact that it technically goes to only to n minus 1 doesn't really matter. And by the way, omega here should be squared. The squared went away somehow. But yeah, it's squared. And yeah, so we have this over here for the propagator. And then here we've just plugged in the determinant. And now what we have to do, right, is we have to always take the limit as n approaches infinity so we can have continuous paths. So let's actually take that limit here. To take the limit, we can notice some things. We can know that this over here should be to the 1/2, by the way. So to the 1/2. So we can distribute the 1/2. This is going to be n over 2. And this 2 pi I will cancel out with this 2 pi I, since like they're both like to the n over 2. And then this m over here will cancel out with the m that should technically be over here. And remember that we did say that there was an m over here. So there should be an m over here, therefore an m over here. So that m will cancel out with that m as well under this same square root. So n over 4. And those are all the things that cancel. So we're pretty much left with the limit. Then we're going to have m to the n over 4 over delta. We can just rewrite this out as all of this to the n over 2, and then 1/2. And then here we're going to have times the product. So product n equals 1 to n of n pi over t squared minus omega squared. All of this to the minus 1/2. Now, there is a problem here because delta, remember, is t over n. So this means that here we're going to have an n over t, and it seems like it's going to diverge. So there is actually a trait that can assure us that it does not diverge. We can use the free particle propagator that you found in the last video. Oh, this isn't the free particle propagator. So here was the path integral for the free particle. The limit as n approaches infinity here, this is just going to be a q. So how can we use this integral, this path integral for the free particle to help us for the harmonic oscillator? Well, we can note that for omega equals 0, we get the propagator for a free particle. Mean that for the harmonic oscillator, or let me just call it the propagator for the harmonic oscillator, is going to be the propagator for the harmonic oscillator times the propagator for the free particle path integral divided by the propagator for the harmonic oscillator, but for omega equals 0. And since these are equal to each other, this is just going to be 1. And this trick is going to help cancel out some of the problematic terms. So actually writing that out, we're going to have it's going to equal, let's just call this over here, let's call this like k or something. So you're going to have k to the n over 2 times this product right over here, n pi over t squared minus omega squared to the minus 1/2. And that is being multiplied by the path integral propagator for the free particle, which is going to be m over 2 pi I t to the 1/2. We're going to stop there because remember, we're looking at the propagator for q not equals 0 and q of t equals 0. So this means that these over here should be 0. So since we're considering the final and initial positions to be 0, which means that this whole thing is just 1. So we're just going to be left with this over here. And then we are going to divide this out by the same thing, harmonic oscillator. So we're going to have k to the n over 2, and this is the n pi over t squared to the minus 1/2. And then when we divide this out, we're going to see that these cancel out. So that's good. And then we're going to see that this will cancel out with this, giving this a 1. And then this is just going to come out to being t omega over n pi all squared. So you're going to be left with 1 minus t omega over n pi squared, or I like omega t over n pi squared, omega t over n pi squared. And that's going to be raised to the minus 1/2, and then times m over 2 pi I t to the 1/2. This product is actually going to be the same thing as omega t over sine omega t to the 1/2. To the 1/2. I don't know how you get that, but it's kind of strange. And then we have times m over 2 pi I t to the 1/2. So that's just carrying out this product over here. I would assume, just by guessing, I would assume that you could get that by expanding out sine of omega t into a product series, so like a series but for products instead. And if you maybe there's some like formula that relates sine of omega t to that sort of product expansion, and that'll come out to being this over here. And then so this is actually our legit answer, And that is our answer for the path integral. So like, how can we signify this? Like, that's our answer for the path integral. So yeah, thanks for watching this video. I hope this video was understandable somewhat. And yeah, in the next video, we'll be solving the path integral for quantum fields. See you guys then. Bye.